To suppress the movement of atoms at room temperature, increasing pressure is an effective method. When pressure is increased, the distance between atoms decreases, and their kinetic energy decreases. This is akin to compressing a ball, making it move less. While increasing pressure effectively suppresses atomic motion, excessively high pressure can break the bonds between atoms, potentially transforming a solid into a liquid or gas. Therefore, maintaining the appropriate pressure is crucial to suppress atomic motion while keeping a solid state. In practice, the use of pressure as a technique to control atomic motion at room temperature finds application in various fields. For instance, in semiconductor manufacturing processes, applying pressure to wafers helps to inhibit atomic motion, allowing for the creation of more precise circuits on the wafer's surface. Additionally, in the production of superconductors, pressure is employed to suppress atomic motion and maintain the superconducting state. Hence, increasing pressure is an effective method for suppressing atomic motion at room temperature. To suppress the movement of atoms at room temperature, increasing pressure is the key. Elevating pressure leads to stronger forces between atoms, causing them to come closer to each other, thus restricting their motion. There are various methods to increase pressure. The simplest approach is to reduce the surface area of an object. For example, compressing a ball makes it flatter, increasing the pressure. Increasing the mass of an object is another way to raise pressure. For instance, by compressing a container filled with heavy objects, pressure can be increased. Raising pressure effectively limits the motion of atoms, but it cannot entirely stop it since atomic motion cannot reach absolute zero. However, sufficiently increasing pressure can slow down atomic motion to a point where it becomes imperceptible. Applications of suppressing atomic motion at room temperature include semiconductor manufacturing. In semiconductor fabrication, controlling atomic motion is essential to align atoms for precise circuitry. Cooling. Elevating pressure lowers temperature. This effect is utilized to create extremely low temperatures in substances like liquid nitrogen or liquid helium. Diamond synthesis. Diamonds consist of carbon atoms strongly bonded together. Increasing pressure brings carbon atoms closer, leading to the formation of diamonds. Therefore, increasing pressure is an effective method to suppress atomic motion at room temperature. To suppress atomic motion at room temperature, increasing pressure is an effective approach. As pressure rises, the distance between atoms decreases, imposing constraints on atomic motion. Consequently, increasing pressure reduces the average free path of atoms, inhibiting their movement. For instance, in the case of air, at 1 atmosphere of pressure, the average free path of atoms is approximately 68 nanometers. However, at a pressure of 100 atmospheres, the average free path reduces to about 10 nanometers. This indicates that increasing pressure results in atoms coming approximately 6.8 times closer to each other. Therefore, raising pressure is an effective method to suppress atomic motion at room temperature. However, excessive pressure can lead to stronger atomic bonding in the transition to a solid state. Hence, it's essential to judiciously regulate pressure to inhibit atomic motion while maintaining a non-solid state. Here are several methods used to suppress atomic motion at room temperature. Pressure. Increasing pressure reduces the distance between atoms, constraining their movement. Temperature. Lowering temperature decreases atomic kinetic energy, suppressing atomic motion. Magnetic fields. Magnetic fields are used to control atomic motion. Electric fields. Electric fields are employed to manipulate atomic motion. By combining these methods appropriately, it is possible to suppress atomic motion at room temperature.